Topcon introduces the KR1W Wavefront Analyzer with 5 functions to support the evaluation of the visual performance of the human eye. The KR1W combines aberrometry, topography, keratometry, pupillometry, and autorefraction in one unit that is unparalleled in terms of functionality and reproducibility. The KR1W's unsurpassed reproducibility and reliability with fully automated measurement and touch panel manipulation make your diagnosis and treatment decision easy. The KR1W can effectively speed up your workflow, improve your communication with patients, and monitor the outcomes of your treatments. The KR1W adds value to your practice. Quickly assess total, corneal, and internal aberrations. Project best corrected vision for optimal contact lenses. Identify complex cases that may require referral, such as keratoconus. Identify helpful information for dry eye and assessment. Improve patient education and case acceptance with the KR1W's informative visuals. Simply touch the center of the pupil on the KR1W and the KR1W automatically obtains right and left eye readings. The KR1W uses a Hartmann-Shack device. Near-infrared light with a narrow band is focused to a point on the fundus. The emerging beam from this point source is focused onto a lenslet array that forms a point pattern that is captured by the CCD camera. The pattern obtained is compared with that of an aberration-free beam, and again the wavefront is computed from the displacements of the points from their unaberrated pattern. After measuring the shape of the wavefront, the Hartmann-Shack wavefront sensor discomposes elements of the light along to the Zernike polynomial. The data from the sensor and images from the KR1W are then displayed on the various KR1W maps. Unlike other topographers that utilize bright lights to image the cornea, the KR1W utilizes invisible near-infrared light with 19 placido rings to collect 6,840 data points to assess the cornea's radius curvature and axial power over the entire 8 mm measurement area. Because topography data is collected at the same time as the wavefront data, no additional tests are required, saving time for you and your patients. Color scale shows the diopter. The colder the color, the weaker the power is. Curvature is flat. The warmer the color, the stronger the power. Curvature is steep. Color scales can be normalized for the subject, absolute is shown here, or customized based on your preferences. The KR1W's Hartmann-Shack sensor measures the wavefront data to calculate spherical, cylindrical, and axis, and presents the data at the actual pupil diameter along with the data at 4 mm and 6 mm. The minimum pupil size for refraction is 2 mm. KR values are displayed just under the axial power map. The KR1W measures the ocular total aberrations with the wavefront sensor and corneal aberrations with the topographer. Since each high-order aberration is expressed by RMS, the internal data can be calculated by deducting corneal data from ocular total data. Aberrations are also measured at each pupil size. The KR1W changes the brightness of the fixation chart to resize the pupil accordingly and measure the aberration at each pupil size. It also measures sphere, cylinder, and axis and higher-order aberration at each or actual pupil size, and thus can simulate pupil size and visual acuity at night when the pupil is bigger. The KR1W has many pre-programmed displays to easily and clearly assess your patient's vision. Maps can also be customized to your specific needs. The multi-map presents a qualitative overview of the patient's vision. From the Meyer, image measurements related to the cornea are analyzed. The date and time of measurement and the pupil diameter are displayed just under the image. Axial power displays the distribution of corneal refractive power. KR values are displayed just under the axial power display. Corneal HOA displays corneal high-order aberration. Just under this display, the corneal high-order aberrations at 4 mm and 6 mm area are displayed with RMS values. The Hartmann-Shack point image is reflected from the retina through the pupil. From this image, refraction values, ocular total aberration, high-order aberration, etc. are calculated. A description about the analysis center is given just under this image. The ocular total aberration display can distinguish near vision tendency and far vision tendency. Refraction values are displayed just under this image. The ocular HOA displays the ocular high-order aberrations. Just under this display shows the corneal high-order aberrations at RMS values at 4 mm and 6 mm. The Landalt's ring simulates the patient's best corrected vision by eyeglasses. Visions of target by 2100.2, 2040.5, and 2020 1.0 are displayed. The Ocular Aberration Map displays the information about aberration related to total refraction. The Corneal Aberration Map displays information related to the total refraction. The color scales of the maps can be normalized or customized based on the user's preference. The Component Map displays the high-order aberrations for the entire ocular system. The Zernike Vector Map displays third and fourth-order aberrations by Zernike components. This point spread function map simulates how a point light source will be projected and spread on the retina with corrected visual acuity at 4 mm pupil size. If there are no aberrations, the light source will be projected as point. MTF quantitatively and qualitatively displays the contrast sensitivity of the eye. The MTF graph shows the contrast sensitivity Y spatial frequency of horizontal direction, Y, blue, and vertical direction, X, red. Y coordinate means contrast sensitivity percentage. X coordinate means how many pairs of white and black lines, stripes, are recognized within 1 degree. The summary map displays high-order aberrations when multiple measurements are done. One possible role for this analysis is to observe tear film break condition with 10 times automatic continuous measurements. The IOL selection map displays information for the application of an IOL after LASIK, selection of K values, spherical IOL and aspheric IOL in determining the power and application of progressive IOL.